Okay, so today we're going to have a look at a further work with applications of vectors to physical situations. Now we've already completed one lesson on this, and we completed the Maths in Focus exercise. This Cambridge exercise is another level up, and it's a bit more realistic in terms of what you're going to see potentially in the HSC. Now, in my opinion, our work here, and especially as well in Extension 2, our work with vectors and forces and mechanics gives you a much more comprehensive understanding of physics than the actual physics subject does. And the reason that is the case is because physics is a non-calculus based course, whereas Extension 1 and Extension 2 are calculus based courses. So to find the magnitude of the resultant forces, so here we've got forces and acting both in the I and the J direction. So we've got forces here acting in 2 dimensions, and we're trying to find the magnitude of the resultant force. Well, first up, to find the resultant vector, let's just call it vector F. We're going to add in the I and J components individually. So 2 plus 4 plus minus 3, we get 3i, so that's in the I direction. And then minus 3 plus 1 plus 3 is plus 1j in the j direction. Now the magnitude of that force is going to be the square root of 3 squared plus 1, which is root 10. So the answer is the square root of 10 newtons. Alright, a classic physics question here from Year 11 Physics. So we've got in the diagram an object of mass 10 kilos is kept at rest on a smooth plane and is inclined at 30 degrees to the horizontal by a force of F newtons acting parallel to the plane. Find the value of F. So here we've got some sort of situation, and we've got an object sitting on an inclined plane and it's not moving. The 2 ways of that occurring is either A, there's maybe a string holding it, but then there would be some sort of tension. So there's either maybe a string holding it, or the force of friction is great enough that it just stays there. So maybe it could be a very small object on a plane with a very high coefficient of friction, so then it's not going to move. Now we want to resolve these forces in the direction of F. And we're going to do that, and the first time I show you how to do this, it's important to know where it comes from. But from after this example, you can just use the identity. So to resolve the forces of this force diagram, first up we're going to consider our weight force, which goes down there, mg. That is our weight force there. We're then going to add in our normal force. So our normal force acts parallel to the object, and it technically acts in the upward direction, but for now we're going to consider the normal force in the downward direction. And then we're going to add in the force we're after. So this F here, it's going to be the same as force F up on the plane, because we can see that it's parallel. Now here we've got a right-angled triangle right here, and this is going to be 60 degrees, which would make this angle here 30 degrees. That's the important identity that we're trying to get out of from this vector resolution scenario here, is that our 30 degrees goes there, which means our force F is equal to mg sine theta. And that's because if we consider this right-angled triangle here, it looks a bit like this. That's mg there. That's what we're trying to find F, and 30 degrees is up here. So it's important to understand, if you haven't done physics before, it's important to understand how that 30 degrees gets to there, and it's through that right-angled knowledge of angle sum of a triangle. 60 degrees, and then using our other 90 degrees to 30 degrees goes up to there. So our force acting in the direction of the plane or parallel to the plane is always mg sine theta. So the mass is 10, gravity is 9.8 times by sine of 30, ensuring that you are in degrees. 10 times 9.8 times sine 30, we get 49 newtons. So the force parallel to the plane is 49 newtons. So that is the force required to keep that object there. Okay, this is the last question in the exercise, and even in terms of HSC physics, this would be a tricky question as well if you don't have a good understanding of it. So we've got in the diagram, it shows objects of masses 3 kilos and 2 kilos connected on smooth planes inclined at angles theta and 2 theta. The objects are attached to the ends of a light inextensible string. Inextensible just means we can't stretch it, and it passes over a smooth pulley. Let T newtons be the tension in the string. And we've got the 3 kilo object is accelerating upwards. Now, importantly, if it's accelerating upwards, that means this object is going up and this object is going down. Now, something that's important about tension is that force in the string. And tension will always act away from the object in the direction of the string. So generally it always is acting towards the pulley. So tension will act this way and this way. Those are our tensile forces. Okay, so we've got to, for part A, find an equation of motion for the 3 kilo object. Well, we know that F is equal to ma. And we also know that the object is accelerating up the plane at a meters per second. So the force of the object going up the plane is its mass of 3 times by its acceleration of F. So the force is equal to 3a. Now, at the same time, the force of this object going up the plane is going to equal the tension in the string. That's the force that's pulling it up. The string is pulling the object up, so the force of it going up is equal to the amount of tension in the string. But we're going to take away the component of the force going down the plane, which in the previous question we have said is always mg sine theta. So 3g sine theta. So the force of this object that's making it, say, move down the plane is always mg sine theta. And the tension, the string is pulling it upwards. So the tension in the string, we're pulling it upward, but we're also at the same time taking away that force that's trying to pull it down. So the resultant is the tension minus that force that's pulling it down. So we can see from this that we're going to have 3a is equal to t minus 3g sine theta. Part B, we've got to write down a similar equation for the motion of the 2 kilo object. Well, this 2 kilo object, first up, it's accelerating downwards. Well, F is equal to ma. Now, it's accelerating downwards at a meters per second. If the 3 kilo object is accelerating up the plane at a meters per second, then since this is a system and it's connected by a single string, the 2 kilo object has to be accelerating down at the same acceleration. So it has a mass of 2 kilos and it's going down at a meters per second. So its force going down is 2 meters per F is equal to 2a newtons. Now at the same time, the force of it going downwards, well, we're going down, we're not going up anymore like the other object. So the force of gravity in the direction of the plane, or the weight force in the direction of the plane, is what's pushing it down. And that's always mg sine theta. Mg sine theta is always, every single time, the component of the force in the direction of the plane. So it's going to be 2g sine, now we're told in the question the angle is 2 theta. So 2g sine 2 theta. But I'm being pushed down by gravity, but that string is holding me up still. So we need to take away the tension from this force. So gravity's pulling me down, but I'm also connected to a string that's stopping me from falling down as fast. Kind of like if you were doing, say, rock climbing and you fell off, you're not going to fall down as fast because you're on a string, and it's going to stop you from falling down as fast, and then it's also going to stop you from hitting the ground. So we're going to take away that tension force. So that tells us that 2a is equal to 2g sine of 2 theta minus t. Okay. Now, part C, we're told, show that the system is in equilibrium when cos theta is 3 on 4. Okay. Equilibrium means it's not moving. So this would be a system in equilibrium. Nothing's happening here. It's in a state of no motion. Now, equilibrium always occurs when your acceleration is 0. And that makes sense. If my acceleration is 0, I'm not really moving. Well, not all the time, but in these questions, if my acceleration is 0, it means we're in equilibrium. So we're going to substitute a0 into both of our equations. Our first equation, 3a, we're just going to have 0 is equal to 2 minus 3g sine theta. Importantly, our acceleration due to gravity is never 0. That can never be 0 on Earth. It's our acceleration we're making 0. And we're also making 0, so we're making this 0, but also this 0 here. So 0 is equal to 2g sine 2 theta minus t. So we can make t the subject of both of these. So from this first one, t, the tension, is going to be 3g sine theta. And then the other one, tension, is going to be 2g sine 2 theta. Okay, so we can just make these equal to each other. The good thing about this question is since it's a singular string, the tension is the same in a singular string. In a question, say, where we've got many different strings, where the tension is different, we might say tension 1 and tension 2. But here we've just got one string, so the tension is the same. So we're going to say 3g sine theta is equal to 2g sine of 2 theta. Now we're trying to find the value of cos theta here, so we might say 2g sine, oh, that's a terrible sign, Tom, 2g sine 2 theta minus 3g, so I'm subtracting this over to the other side. I don't think it would matter if you subtracted 1 over to the other side, it means the same thing. 3g sine theta, and that's equal to 0 now. Now remember, sine of 2 theta is 2 sine theta cos theta. So this is 2g times 2 sine theta cos theta minus 3g sine theta. So this is going to be 4g sine theta cos theta minus 3g sine theta. Now, here we can see that we can take out a factor of sine theta g, or g sine theta, and then we've got 4 cos theta minus 3 equals 0. So that's telling us that g sine theta equals 0, or 4 cos theta minus 3 equals 0. Now, g sine theta can't equal 0. We can't have that being 0. So 4 cos theta minus 3 equals 0, which means cos theta is equal to 3 over 4. And we're done. Alright, hope that makes sense. Thank you.